Hello, and thank you for joining me for some more reinforced concrete design. In this session, we will discuss redistribution of moments. Steel is an elastoplastic material, while concrete is a plastic material. Therefore, reinforced concrete behaves in a manner in between that of steel and concrete. The resulting behaviour of reinforced concrete depends on relative quantities and individual properties of both materials. We already established that reinforced concrete structures do not behave elastically. However, elastic global analysis is generally used in their design. This approach is accurate for low levels of stresses corresponding with a serviceability limit state. However, it is not accurate when plastic deformations occur, which corresponds to the ultimate limit state. Eurocode 2 allows to take the plastic behavior into account through the redistribution of mending moments obtained from elastic global analysis. Let's consider the plastic behavior of a continuous reinforced concrete beam using a moment curvature curve. The curve can be divided into a few parts, the limits of which correspond to the development of the first crack, first yielding of reinforcement, and the development of a plastic hinge. The rotation of this hinge is limited by the concrete crushing. After the plastic hinge is developed, the moment remains constant while the curvature grows. The additional load is redistributed to less loaded members. The development of a plastic hinge results in a change of the static model by reducing the order of static indeterminacy. Further hinges may develop in this beam. Let's now consider an example of plastic analysis on a single span fixed end beam under uniformly distributed load. The elastic moment at the support is the UDL times span over 12, while the elastic moment at the midspan is twice smaller. We also assume that the ultimate bending resistance of the beam at supports equals to the ultimate bending resistance of the beam at the midspan. Additionally, we assume that adequate rotation of hinges is possible. With increasing load, the bending moment at the supports will reach the ultimate bending resistance mu, where W is the UDL, causing the development of plastic hinges at the supports. After the development of plastic hinges at the supports, the beam behaves as a simply supported beam. The simply supported beam is statically determinate and fails by reaching the ultimate bending resistance at the midspan, which corresponds to the development of an additional plastic hinge. At this stage, the bending moment at midspan consists of two parts. The first part is the bending moment corresponding to the stage when the plastic hinges developed at supports. This moment equals to WL squared over 24, which is half of the ultimate bending resistance moment, mu. The second part represents an additional bending moment causing the development of a plastic hinge at the midspan and is equal to mb WA times L squared over 8, where WA is the additional uniformly distributed load. The second part represents an additional bending moment causing the development of a plastic hinge at the midspan, which is equal to mb WA times L squared over 8, where WA is the additional uniformly distributed load. We assume that the ultimate bending resistance at the supports and midspan is similar. This leads to the following equation. The solution of this equation results in WA equals W over 3. As a result, the total uniformly distributed load causing failure of the beam is 33% higher than the uniformly distributed load causing the development of plastic hinges at supports. The elastic structural analysis method regards the development of plastic hinges at supports as structural failure. Therefore, the 33% increase of the load carrying capacity of the beam due to moment redistribution represents the difference between the elastic and plastic structural analysis methods. The plastic analysis consists of identifying the development of plastic hinges and incorporating these hinges into the structural model until the model becomes a mechanism. In the example we discussed, we had two stages. At the first stage, hinges developed at supports, changing the structural model from fixed end to a simply supported beam. In the second stage, a hinge developed at midspan, changing the structural model into a mechanism. The plastic structural analysis can become very long for structural models with high order of static indeterminacy. An alternative method for calculating bending moments is based on the elastic structural analysis, followed by the redistribution of moments. In the case considered, we first find the bending moment diagram of the elastic fixed end beam loaded by the total uniformly distributed load. Then we reduce the support moments to the ultimate bending resistant moment and increase the midspan moment until it equals the ultimate bending resistant moment. As you can see, this analysis procedure is easier than the two stages of plastic structural analysis. In a continuous beam, support moments are usually larger than midspan moments, and therefore they are redistributed. On this slide, you can see the redistribution of the bending moment above the middle support, which leads to the increase of midspan moments. Usually, the redistributed part of the support moment is larger than the increase of midspan moments. The design with redistribution starts with the derivation of the elastic bending moment diagram. Next, maximum support moments are reduced. This leads to saving on the amounts of steel needed and a reduction of reinforcement congestion at beam column intersections. Span moments are increased to maintain static equilibrium of the structure. The process of moment redistribution should assure that the equilibrium of the internal forces and moments is maintained. This leads to recalculation of span bending moments and shear forces for the load case involved. Moment redistribution can be performed on continuous beams and slabs because they predominantly work in bending. The ratio of adjacent spans should be in the range of 0.5 to 2. Columns should be designed without redistributing the moments applied. To be able to recalculate span bending moments and shear forces after redistribution of a support moment, we need to develop relationships between the moment at midspan and the moments and shear forces at supports in a typical internal span of a continuous beam under a uniformly distributed load. Let's consider a typical span AB of a continuous beam under a uniformly distributed load. The corresponding shear force and bending moment diagrams are shown on this slide. In the diagrams, VAB and MAB are the shear force and bending moment above the support A, while VBA and MBA are the shear force and bending moments above the support B. The equilibrium of moments about the support B results in the following equation. This equation can be solved for the shear force VAB. The shear force VBA can be found from the equilibrium of vertical forces. The maximum span moment Mmax occurs at zero shear. The distance A3 to zero shear from the left support can be found from the left triangle on a shear force diagram. In this expression, the UDL represents the rate of the shear force reduction per metre length. The maximum span moment can be found by considering the rotational equilibrium of the left part of the beam of the length A3. This leads to the following expression. The location of the points of contraflexure can be found by considering that at this point the bending moment equals 0. This leads to the following quadratic equation. The quadratic equation describing the points of contraflexure has two roots, describing the positions of the 2 points in the span AB. The expressions for the locations A1 and A2 of the points are given on this slide. The analysis assumes that beams rest on point supports. However, in real structures, beams are supported by columns, which have width. As a result, actual moments above the supports are lower. As you can see, the moment in the middle of the support is lowered by the shear force in the support times the support width divided by 8. The moments at the left and right faces of the support are further reduced due to the support width. It can be approximately assumed that the moments at the support faces are equal to 90% of the point support moment. Note that these considerations are usually disregarded in the design, making it more conservative. After understanding what moment redistribution is, we can discuss the process of design with redistribution established by Eurocode 2. As we discussed, redistribution of loads occurs due to the formation of plastic hinges. As a result, plastic hinges in reinforced concrete beams require relatively large rotation with yielding of tension steel. Eurocode 2 ensures large strains in tension steel and sufficient rotational capacity of plastic hinges by limiting the depth of the neutral axis according to the magnitude of moment redistribution carried out. The limiting value on the depth of the neutral axis of normal strength concrete is governed in Eurocode 2 by the parameters delta, K1 and K2. Here, the depth of the neutral axis is defined through the x to d ratio. The parameter delta is defined as the ratio between the moment at a considered section after redistribution to the moment before redistribution and cannot be larger than 1. Eurocode 2 sets the parameters K1 and K2 equal to 0.44 and 1.25 respectively, while they're corrected to 0.4 and 1 by the UK's National Annex. Applying a limit on the depth of the neutral axis limits the maximum moment that the design reinforced concrete section can carry. When a rectangular stress block method is used in design, the limit value of bending moment and corresponding parameter K can be found as shown on this slide. In this expression, both the lever arm and the depth of the stress block depend on the depth of the neutral axis. The limit value of the parameter K can be represented as the product of the x to d and z to d ratios. Substituting the relationship between the x to d ratio and the parameters delta K1 and K2 results in the following expression for the parameter K. The design proceeds further with reduced values of parameter K and the maximum bending moment in the section. Compression reinforcement is needed when the design moment and corresponding parameter K are larger than the limit values. The design of reinforced concrete beams aims to ensure enough ductility in the regions of yielding hinges by limiting the height of the neutral axis. The x to d ratio is limited to 0.45 for beams made of normal strength concretes. The high strength concretes are more brittle than normal strength concretes. To compensate lower ductility of high strength concrete beams, their x to d ratio is limited to 0.35. The redistribution requires the regions with yielding hinges to have sufficient ductility. It is assumed that the redistribution of up to 15% does not affect the ductility in the regions of yielding hinges. When more than 15% bending is redistributed, the limit of the x to d ratio is reduced to ensure additional ductility of the regions of yielding hinges. The redistribution can be carried out only when sufficient rotational capacity of a plastic hinge is assured. In continuous beams and one-way slabs, the length of the plastic hinge zone is assumed as 1.2 times the structural height. According to Eurocode 2, the rotational capacity of a hinge at the ultimate limit state is limited to the product of basic value of allowable rotation, theta PLD, and the correction factor K lambda. The correction factor K lambda depends on shear slenderness, which is the ratio of the distance between the point of zero and maximum moment after redistribution and effective depth. The basic value of allowable rotation, theta PLD, depends on the reinforcement type, concrete strength, and the x to d ratio. Fire can soften reinforcing steel at supports, which leads to the increase of rotation at hinges at supports and the increase of span moments. If redistribution exceeds 15%, fire-resistant beams must be designed at midspan as simply supported. This can offset any reinforcement-related savings at supports. Thank you for joining me. I hope you found this session on redistribution in reinforced concrete design helpful. In the next sessions, we will discuss design of beams, slabs, and columns before looking at detailing according to the Eurocode. I hope you join me for that.